Okay, I just recorded a video for my Ever class and all in one shot. So let's see if my luck can continue um, with this one. So the last topic with regard to convergence analysis is on what are called stiff differential equations. Now for this part of the section 12.4, there are no exploration problems to do, but the quiz for this section does have some questions about stiff differential equations. So I need to cover at least uh, uh, material for those questions. Um, what does it mean for an ODE to be, or a system of ODEs to be stiff? Um, so there are different definitions that are all equivalent in some sense. There's no formal definition per se, um, but it's basically a more qualitative property of the solution of a differential equation. Um, so an ODE is stiff if its exact solution. So this is a property of a problem, not to numerical method, but it's certainly something that causes problems for numerical methods in general. If its exact solution, okay, so I'll have y prime. No, I want an actual dollar sign. Y prime equals f of t y is stiff if its exact solution, y of t, um, has terms in it that decay to 0 as t goes to infinity. So there are terms that don't really make much contribution to the solution in terms of what you would see on a graph, um, but have very large derivatives. Okay. So as an example, a term of a form e to the minus ct, where c is large. For the derivative is actually, I should say the kth derivative is c to the k, minus c to the k e to the minus ct. So what happens is if c is large, then this constant gets large in magnitude. So even though for c large, this function is very small unless t is near 0. So if this is a mix of other terms in the solution, the contribution to the solution from this term would likely be uh, negligible. But because the derivative can be large, we have to keep in mind that a time-stepping method, whether it's multi-step or one-step, of let's see, p order accuracy. So the accuracy is of order h to the p is the error. Of error formula involves a derivative. So, for example, a first-order method, Euler's method, has y double prime in the error. So we have the p plus first derivative of a solution. So that means that if its exact solution includes a term like this, so you have this constant, minus c to the p plus 1 for a p order method, that could mean the error could be large. So this is something that we must be mindful of in the design of numerical methods. And I'm going to give one other notion of stiffness. One might also take it as an alternative definition. That the time step necessary to compute the solution correctly, in other words, a solution that behaves in the correct way, qualitatively, like it decays to 0 when the exact solution decays to 0, etc. is far smaller. So we're talking about the value of h that we use as a time step is far smaller than the time step h needed to depict, or another word might be better is a represent the solution, like on a graph. So in other words, most of the solution is very smooth, at least if the terms that are not negligibly small, but has small terms with large derivatives, like this e to the minus ct. So if you're looking at a plot of the exact solution, you might think, oh, that's a smooth function. You don't need many points to represent it accurately with a smooth curve. So maybe you can get away with a large value of a time step h, but it turns out you can't. You need a much smaller h than the appearance of a solution would suggest. Now, why is this a problem? Stiff ODEs are a problem because they require a small value of h, which, so if you're taking more time steps that are smaller to get to your final time, then that's more computational effort, because the amount of computational effort is proportional to the number of time steps that you're taking. So the work per time step may not be much, but it really adds up. So the overall computation time is increased. And this is not only a problem just for ODEs, but in particular, systems of ODEs that arise from PDEs, partial differential equations. So that's what my research is all about. So the systems of ODEs that come from PDEs generally are stiff and require these small time steps to solve accurately. And this is one reason, as we'll see, why implicit methods are often in favor for such problems, because you may still need to use a small time step, but not as small as what you would need from an explicit method. Okay, so I'm going to give an example of a very simple ODE that that requires a small time step. So y prime is equal to minus 100y, and the initial condition y is 0 equals 1. So the exact solution is y of t is equal to e to the minus 100t. So if it's something that decays to 0 very quickly because of that 100 in the exponent. So to give you an idea, if I were to say at time 1, so t equals 1, if I take the exponential of that, it's practically 0. It's far smaller than even machine precision. It's on the order of like 10 to the minus 44. So very rapid decay. Let's consider Euler's method applied to this problem. So yn plus 1 is equal to yn plus h times, so this is my function f of ty, so minus 100 yn. So I can factor a yn out of this, and I get 1 minus 100h times yn. So to go from time n to time n plus 1, I'm just multiplying by 1 minus 100h. So if I let h be equal to, let's say, 0.1, seems like a reasonable time step, then we have yn plus 1 is equal to 1 minus 100 times 0.1, so 1 minus 10. So minus 9 y to the n And in general, yn is equal to minus 9 to the n times y naught, but the initial value is 1. So, so that's my numerical solution. Well, the exact solution decays to 0 very quickly. This grows exponentially, so it's way, way off. Instead, if I let h equal 10 to the minus 3, then yn would be equal to, so my multiplier is going to be 1 minus 0.1, so 0.9, 0.9 to the n. And that's a lot more reasonable. It's at least decaying to 0. It's not decaying to 0 nearly as rapidly as the exact solution does, but at least it's in the ballpark. So we must choose a small time step to have any hope of getting reasonable accuracy. So really we need even smaller h. Okay. So what we'd like to be able to do is get an idea for a general one-step or multi-step method. How small does h need to be for a particular problem to ensure a qualitatively correct solution? So I'll go into a new page here. So to analyze methods for purpose of determining we use the test equation. Very simple ODE. Y prime is equal to lambda y. And so lambda is a constant, but one thing about this constant is the real part, we assume the real part of lambda is negative. So that way we know that the exact solution is going to decay to 0 as t goes to infinity. Now, the reason why we're focusing on exponential decay rather than exponential growth is if you have a ODE whose exact solution exhibits exponential growth, it's actually not a well-posed problem. And the reason for that is it does not satisfy the third condition for well-posedness. The solution must depend continuously on the data. For a problem where the exact solution grows exponentially, if you change the initial data a little bit, then that change will be magnified exponentially in the solution over time. So we can't really call it a well-posed problem. So we're focusing on well-posed problems that feature exponential decay, which we generally see for physical phenomena like heat diffusion, for instance. And the initial condition, y is 0 equals 1. So we know the exact solution. Y of t is equal to e to the lambda t, and because lambda has a real part that's negative, it's decaying to 0. Now, but the problem is this. But if lambda, I should say the magnitude of lambda, or I should say its real part, really, not so much the imaginary part, if that is large, then this ODE is stiff. Now, what we could do is we could take a given numerical method, like a one-step or multi-step method, and apply it to this problem. So it'd be fairly straightforward to work out what the computed solution would be. And then we want to make sure that h is small enough so that the computed solution behaves as it should, that it exhibits that exponential decay. So what happens is, first I'm going to discuss one-step methods. So the idea is when applied to the test equation, it always simplifies something of this form. Y n plus 1 is equal to some function q of h lambda times yn. In fact, we could say something more, where so q, well, first interruption of recording. Let's see how many more we'll get. All right, so q of h lambda, the function that defines the explicit not explicit, one-step method as implicit or explicit, is either a polynomial if it's explicit or rational function, so a quotient of polynomials if it's implicit. It is an approximation of the exact solution operator. So that would be e to the lambda h. So for instance, if it's an explicit method, then this function q of h lambda might be first part of the Taylor series for the exponential, or might match it up to a certain point. So we require exponential decay, meaning that e to the lambda h must be less than 1. So we require, so this is a condition that, wow, got a whole minute in before it stopped again. So for a one-step method, to have exponential decay in a numerical solution that matches what we see from the exact solution, this condition, the absolute value of q of h lambda, must be less than 1. So what this means is we have to choose h small enough so that for whatever value of lambda we have, for example, lambda might be the maximum of our f of ty, or time derivative, that if we can show that this is satisfied, then we know that we will get a qualitatively correct solution. So that's what we're aiming for. To get this essential behavior of the exact solution. So that's really what this is about. And hopefully we get high accuracy as well. And certainly we can always choose h small enough to achieve that, but we don't want to choose h terribly small just because, then again, it's more computational effort. But we want to find a minimum computational effort that is needed for whatever method we're using to get a physically reasonable solution. So if I do an example of this for a one-step method, the modified Euler method. Okay, so that would be all right. I don't know if I've brought up the modified Euler method in these notes before, so I'll just route to general method. So that'd be f of t n y n plus f of, actually, you know what, I have brought up this method before. I refer to it as by a different name. Okay, yn plus f. Okay, so I have referred to this method by a different name, the explicit trapezoidal method. So evaluate f at time tn, and then at tn plus 1, so tn plus h, and then yn plus h, f of tn yn. So this is an approximation of f of tn plus 1, yn plus 1. It's just computed explicitly. The implicit trapezoidal method, I have yn plus 1 in place here. That makes it implicit. Okay, so if we apply to the test equation, what I have is yn plus 1 is equal to yn plus h over 2. And I have, for f of t and yn, that's just lambda yn plus, for the other part, I'm going to have lambda applied to this part. So I'm going to have lambda times yn plus hf again, but that's also lambda yn. Okay, so now I need to simplify that. Notice yn factors out of everything. So what's left? I'm going to have 1 plus h lambda over 2 from here, and then h lambda over 2 again from there. So I'm going to have h lambda, those two terms combine. Okay. And then what I have is 1 half h squared lambda squared. Now you might recognize this. This is the first three terms of the Taylor series for e to the h lambda. So it matches, and this is why we can see that the method is second order accurate. Now, in order to ensure that q of h lambda, which is what's multiplying yn, so it's 1 plus h lambda plus 1 half h lambda squared. Okay, so we need this. So we need this to be less than 1 in absolute value. So how can we go ahead and do that? So this has to be between -1 and 1. Okay, so so for what interval would that actually be the case? So so if I let x equal h lambda for convenience, so what we have is -1 is less than 1 plus x plus 1 half x squared is less than 1. Or what I could do is I could add 1 to all sides. So if I add 1 to all sides, then I get 0 here, and I get 2 here, and 2 here. Now keep in mind, x is h lambda. H is positive, lambda is negative, so x is actually going to be negative. So what that means is, so this has to be negative for one thing. Must have x plus x squared over 2 be negative. So subtracting something off from 2. Also, we must make sure that not only negative, it's not so negative that it goes past 0. So we don't want to have x plus 1 half x squared greater than -2. So how can we ensure that? Well, from this part, we can go ahead and factor an x out. So x and then 1 plus x over 2 must be negative. Now, x itself already is x already is negative. So we must ensure that this part remains positive. So 1 plus x over 2 is greater than 0, or put another way, x is less than -2. So we have x must be between 0 and -2 for one thing, and then we also have this part right here. I'm going to rewrite this. 1 plus x squared over 2. Okay. Now, okay, so what happens here is suppose x is between 0 and minus 2. Then x squared will be between 0 and 4. X squared over 2 will be between 0 and 2. So if I take something that's already between 0 and minus 2, and I'll add something to it, at least it will be something that's greater than minus 2. So if this first part is satisfied, this part will be satisfied as well. So we must have, for this method to have a qualitatively correct solution, 0 is less than h lambda. Therefore, the larger lambda is, so for instance, if f, your function f of ty from your ODE, can be large in magnitude, h must be small enough, okay, put absolute value around that, okay, because remember h lambda is negative, as I said. H must be chosen small enough so that the product in magnitude is between 0 and 2. So that's a pretty stringent restriction on H, especially for the kind of systems of ODEs that come from PDEs defined at a high resolution. But you might need a really, really small value of H just to get a reasonable solution. Now, this is an explicit method. Explicit methods tend to require smaller values of H than implicit methods do. Okay, so that's one-step methods. Now, for multi-step methods, we have the following. If we apply to if we apply a general multi-step method equation, then we have the following. We have some I goes from 0 to m of alpha I, y, n plus 1 minus I. That's equal to h 0 to m. And then we have beta I, and then f value, but that's just going to be lambda times y n plus 1 minus I. So really what I can do is I can move everything onto one side, and I'll get alpha I minus h beta times all these y values is equal to 0. So what we have, kind of similar to a discussion of stability for multi-step methods, we have a recurrence relation. But it's a different recurrence relation from before. Before it was not y prime equals lambda y, it was y prime, oh, sorry, I forgot the lambda. Let me put that in here. Okay. Before it was y prime is equal to 0, so we didn't have this part here, just the alphas. We got a characteristic polynomial of a recurrence relation, and required it to have roots that were less than or equal to 1 in magnitude. So this recurrence relation has the characteristic equation. Okay, so we have alpha 0 minus lambda, or h lambda, beta 0, lambda to the m. Okay, actually, I used lambda before. I need to use a different symbol now. So mu. And I'm going to call this entire polynomial q of mu with parameter h lambda. So h lambda affects the coefficients, but it is a polynomial in mu. So we have the other coefficients, so alpha 1 minus h lambda beta 1 mu n minus 1, and we keep going all the way down to the last coefficients. So we have alpha m minus h lambda beta m. And that must be equal to 0. So that's a characteristic equation. So as before, in order to make sure that solutions of this recurrence relation, in other words, the y's, do not exhibit exponential growth, in fact, we really want exponential decay. So to ensure, so it's stronger than the root condition we saw before. To ensure exponential decay, we must have all the roots of q of mu h lambda okay, and I'll call these roots mu I. So we must have these roots be less than 1 in magnitude. All right, so very different conditions for multi-step methods versus one-step methods. For a one-step method, the method itself defines a stability function. That's just a q of h lambda, and it must be less than 1 in magnitude. But for a multi-step method, whether the method is implicit or explicit, we get this polynomial here, and that polynomial has a name in this setting. Okay. It's called a stability polynomial. So this q v mu h lambda, this polynomial here is called a stability polynomial of a multi-step method. So for a given choice of h and lambda, if a stability polynomial that you get from your multi-step method has roots that are less than 1, then we have exponential decay. So don't get the classes of methods confused. So we get a function q of h lambda in both cases, but for one-step method, it's only dependent on h lambda. The function itself must be less than 1 in magnitude. For multi-step method, it's a function of h lambda, but really it's a polynomial in another variable mu. The roots mu must be less than 1 in magnitude in this case. So you're always looking for something to be less than 1 in magnitude, but very different things between one-step and multi-step. Okay. Now, I want to do an example involving a multi-step method. A three-step Adams-Bashforth method, so it's explicit, n plus 1 is equal to yn plus h over 12, and what we have here is okay, 23 fn minus 16 fn minus 1 plus 5 fn minus 2. Okay, so that's our three-step method. So the stability polynomial, so that'd be q of mu h lambda. So to get to coefficients, we have alpha 0 is 1, alpha 1 is minus 1, and then here are the betas. Beta 0 is 0 because it's an explicit method. Here's beta 1, here's beta 2, and here is beta 3. Don't forget to divide by 12. That's part of it. So for our first coefficient, it's going to be alpha 0, which is 1, minus h. Sorry, I forgot the. Well, the lambda comes from the f. Okay, so the so I have alpha 0 minus h beta 0. But beta 0 is 0 because this is an explicit method. So my leading coefficient is just 1. So that'll be mu cubed is my leading term. So we have a coefficient 1. That's going to be true for explicit Adams methods or Adams Bashforth methods in general. That the leading coefficient is just 1. Then for the next term, I have alpha 1, which is minus 1. And then I have minus h lambda times beta 0, which is 23 over 12. Okay, and times mu squared. Then the next term, I have no other alphas. It's only betas from this point on. So I'm going to have minus h lambda times beta 1, which is minus 16 twelfths. Well, that causes this to be a plus. And I'm going to have a 16 twelfths or 4/3 h lambda, and that's times the next power of mu, which is this mu to the first. And then for the constant term, I have, well, alpha 3 is 0, so I have minus h lambda times beta 3, which is 5/12. So I'll put that right here. Okay. And that's the constant term, so I have nothing else. And so that's the entire function, the stability polynomial. That's of degree 3 because it's a 3-step method. Now the problem is, for most multi-step methods, it's not easy, or maybe not, it's not possible to analytically compute the roots of a stability polynomial. So really what you could do is you can plug in values of h and lambda. So as an example, I'll let lambda, so focus on a specific problem, equal minus 100 like we saw before. If I choose, say, h equals 0.1, the largest root that we have is roughly minus 18. So it's way out of bounds. We need the roots to be less than 1 in magnitude. So h equals 0.1 is too large. Choose 0.005. Then all roots are less than 1 in magnitude. So that time step was good enough for lambda equals minus 100. Now here, h lambda in this case would be equal to minus 0.5. So if you choose a larger lambda in absolute value, you must choose a smaller h to compensate. Okay. All right. Now, so the idea of finding values of h and lambda that give you a viable solution for one-step or multi-step method, this leads to what's called the region of absolute stability. So what is a region of absolute stability? Okay. Region of is a region lambda in R works. And what that means is for a multi-step method, Q of H lambda is less than 1, or step method q of mu and h lambda as roots less than 1 in magnitude for a multistep method. So whatever kind of method you're using, the viable choices of h lambda is now thought of as a single variable. The portion of a complex plane that h lambda can sit in to make whichever one of these methods work, that is a region of absolute stability for a given method. So region of absolute stability of a one-step or multi-step method. Okay. Now, we're primarily interested in the left half plane, where the real part is negative, because that's what we have from a test equation. The region of absolute stability can spill into the positive part, but it's really the negative part that we're most interested in. So if a region of absolute stability R includes the entire left half plane, so real part negative, then the method is astable. So we like astable methods because then you can pretty much choose whatever h you want for whatever lambda you want, and it doesn't matter. You're going to get a solution that behaves reasonably, at least in a qualitative sense. There are not many astable methods, though. There is an example, a simple astable method is backward Euler. So yn plus 1 is equal to yn plus h lambda yn plus 1. So if I apply this directly to the test equation, then this is what I get. Or put another way, yn plus 1 is equal to one over 1 minus h lambda yn, just by rearranging. Now, the thing is, for multiplying by this number, keep in mind that lambda has a negative real part. So, so for real part, I'm adding something onto 1. So the denominator is automatically going to have a larger magnitude than the numerator. So for any lambda with its real part being negative, we have 1 over 1 minus h lambda is strictly less than 1. So 1 over 1 minus h lambda, that is the q of h lambda that this one-step method has. So it is astable. Because wherever it's less than 1, q of h lambda is less than 1, that h lambda is in the region of absolute stability. Since any h lambda with real part of lambda negative and h is positive is in the region of absolute stability, the region of absolute stability occupies the whole left half of a complex plane. Therefore, backward Euler is astable. Another method is shown in the book that is also astable is the implicit trapezoidal method, which is nice because that is a second order accurate method, whereas backward Euler is only first order. Okay. All right, but it's actually been proven that there's limitations on what methods can be astable, and that leads to what are called Dahlquist barrier theorems for multi-step methods, which is what these barrier theorems apply to. We've already seen Dahlquist had another theorem for multi-step methods, the Dahlquist equivalence theorem, which states that a consistent method is convergent if and only if it is zero stable. So other theorems that he had for multi-step methods. First, barrier theorem is a limitation on how high the order of accuracy can be for a zero stable method. So if a multi-step method is zero, and I'll be more specific, is an M-step multi-step method is zero stable, then its order of accuracy is at most m plus, dang it, m plus 1 if m is odd, and m plus 2 if m is even. Now, zero stable, it can be strongly or weakly, but if a method is stable at all, then there's this upper bound on the order of accuracy of method. In other words, it is possible to have higher order accurate m-step methods, but then you give up zero stability. And one example of where the barrier is hit is a method I showed last time. Simpson's method is a two-step method that is fourth order accurate. It is zero stable, just weakly so. So it's m is equal to 2, its order of accuracy equal to 4. So it hits the upper limit. Adams methods in general that are m-step are order of accuracy only m if it's Adams batch form. It is m plus 1 if whether it's regardless of whether odd is or m is odd or even in the case of an implicit Adams Moulton method. So there aren't any Adams methods that hit this barrier, unfortunately. Okay, now the other theorem is about astability. So the second barrier theorem says a number of things. There is no such thing as an explicit astable method. So any astable method we see has to be implicit, such as backward Euler or the implicit trapezoidal method. Also, there is no astable method of order greater than 2. So implicit trapezoidal method, which is second order, that's the highest order of accuracy you can possibly get with the astable multi-step method. Okay. Also, among astable methods whose order is equal to 2, so the astable second order method with the smallest asymptotic error constant. Now remember, all error formulas for these time-stepping methods, what do they include? They include a power of h, they include a higher order derivative of y, and then there's some constant factors. So the astable second order method with the smallest asymptotic error constant is the method I just talked about, the implicit trapezoidal method. Okay. So it's an optimal method in that sense. So that completes convergence analysis. And I'm so glad that the recording completed. Dang it. Or it seems to be some sort of LaTeX error in here somewhere that's going to drive me batty. Oh, I know what it is. Okay. Okay, that fixed it. So that completes my coverage of convergence analysis. Next time we're going to look at time-stepping methods for systems of ODEs and also higher order equations. We've dealt with y prime equals f of ty, first order. And what about something involving y double prime? How do we handle that? So I will, well, I won't see you on Monday, but at least I'll cover this for you on Monday.